Today's last lecture on motors, and starting next week we'll do, as I mentioned, system design, because now you know already the three components: the sensors, the interconnect, and the actuators. So we'll spend a couple of lectures on system design, if you're given a problem, how to approach it overall, and that should be quite useful, I think. But right now I just want to add a few little bits of information about motors, and the first bit of information is I want to explain intuitively what happens in an induction motor, because I noticed that there are many videos on YouTube about electric motors. You can look on YouTube, how does a DC motor work, how does an induction motor work, and there's also many popular books. I noticed that all of them give the wrong explanation, because in a synchronous motor it's actually quite clear what's happening, because in a synchronous motor you have the equivalent of magnets which rotate, and these magnets rotate, then you have an armature which is attracted to the rotating magnet and dragged along with them. Okay, so it's very easy intuitively to understand what's happening in a synchronous motor, because you just envision this is a rotating field, it drags the armature with it, it drags it with a little bit of a spring action, which is called the power angle. It's the same as a stepper motor, right? So this is very clear. Now, in an induction motor, most books and all videos I've seen say something similar is happening. They say that there is a rotating field which, because it's AC, induces a current in a short-circuited armature. Okay, and this is a squirrel cage, as I discussed before. It's a block of metal, block of iron laminations covered with copper or aluminum to make a short-circuiting coil. Since it's short-circuited, it doesn't have to look like a coil. It can be just a block of conductor. And somehow all the videos say that there is an induced current here, because this is actually an AC current. These are actually coils. So there is an induced current here which causes a magnetic field, and this magnetic field interacts with this magnetic field. So you back to this model. You have two magnets. This rotating field is pulling the electromagnet, but of course it has to pull it with some slip, because if it pulled it synchronous, there will be no induced current, right? Because if this follows the field exactly, it always sees the same magnetic field, so there is no delta phi to delta t, there's no induced current. Okay? But that's actually not what's happening, because, I mean, it's good enough an explanation to derive the graphs and so on, but that's really not what's happening, because you learned before in this course about Lenz's law. Right. And I'm reminding you of the demo of the copper pipe that I dropped a magnet in, and the copper pipe slowed down the magnet. Okay, and the explanation was, why did the copper pipe slow down the magnet when you dropped it in? So, come on, somebody must remember. What's the explanation? Yeah.
Produces opposing.
Exactly, because there is something called Lenz's law, which says that any current created by a changing magnetic field will try to oppose this field. It will try to create a field which is opposed to this field. So if you drop a magnet through a copper pipe, there will be currents induced, and these currents will try to form a magnet which is opposing polarity. Okay? However, if the magnet will stand still, the currents will stop, because these currents are caused by change of flux. Okay? Times n, where n is here 1. So if the magnet stops, there is no change of flux. So the magnet has to keep moving to create this current, but slower. Okay? Now, another analogy is, if you have a block of copper on wheels on a cart, and then on another cart you put a big magnet, and you push this cart towards the cart which has a block of conductor, what will happen? So at the beginning, this will induce a current here and repel it. But it cannot repel it at a constant, it cannot keep this distance constant. Because if it repelled it and kept the distance constant, this will see a constant flux. Because remember, this magnet has a flux. Now, this only created a current when it felt a changing flux. So if you push it, this gap cannot stay constant, because constant meaning constant flux, meaning no d phi to dt. Okay? So as you do this experiment, you'll see the magnet will get closer and closer to the card until they touch. And then you just push it mechanically. But while it's pushing it magnetically, the distance has to come closer and closer and closer, because the magnetic field has to keep changing in order to generate a force. Okay? So if we look at the induction motor, what the current created here must oppose the field which created it by Lenz's law. So actually, unlike here, where the magnet is dragged by the rotating field, here it's the other way. Is this magnet and the rotating field repel each other. Because think of this as a simple analogy. Think instead of a rotating magnetic field, a linear moving magnetic field and a piece of conductor. So in a linear moving magnetic field, a piece of conductor, it will repel it. However, there has to be slip. If this moves at velocity v, this has to move at velocity v minus delta v, because if the velocities are the same, there is no change in field. Okay? So the slip in the induction motor is caused by the fact that for this to see a changing field, it has to lag behind the rotating field. Okay? So another way of looking at it, when this field rotates and this is stationary, the induced current is trying to stop the rotating field. Exactly like this, trying to stop the magnet. But it cannot stop the rotating field, so instead it's being pushed ahead. In other words, if something coming at me like a magnetic field, and I want to stop it, because Lenz's law is trying to stop it, but if this is coming at great force, I cannot stop it, I'm being pushed back. So this is being pushed back by the approaching magnetic field, and there is some slip, there is some delta V, but what this is trying to do is trying to stop the magnetic field, but it's being pushed back. So the effect is the same as here, in a sense that you have a power angle, you have all the same effects. Actually, in this case, not a power angle, it's continuous slip, but the only difference is that in a synchronous motor, the magnetic field attracts the opposite poles of the rotor and drags them along. And here, the rotating magnetic field actually repels the rotor. But because the magnetic field has to go faster in order to generate a delta F, it looks that the rotor is lagging behind. It's always falling behind, so it appears as if this is dragging it. Because you see, one of them, the rotating field, goes faster than this is following, but it's actually not following. It's being pushed ahead with a slip. The same way here, as this is being pushed ahead, but it's falling closer and closer to keep the magnetic field changing. Okay? Now, is this explanation clear to everybody? Good. Okay. Now, I'll show you something which doesn't appear to be related to an induction motor, but it's quite fascinating, and you'll see in a minute why it's related. So for that, I have to press the screen to start. Okay. Projector presentation, and okay, let it power up. Okay, good. So if you take an electromagnet, if you take an AC electromagnet and you put on it a piece of copper, okay, and you turn on the power, what will happen to the piece of copper? First it will heat up because it's a transformer. There is an induced current, so that's a good answer. It will heat up. There are some kitchen cooktops which work like that. They're called induction cooktops, right? Yeah, what else will happen to it? So you put a big current in here. Will it be attracted, repelled, or nothing? Yes? Repelled. Actually repelled quite violently. Because if there is a big current here, the forces can be very big. It actually shoot up. Okay? Matter of fact, there is some all kinds of futuristic rail guns which work on this principle. But anyway, so here is an electromagnet. Okay, let's get to document camera. Okay, and get to some light. Okay, so if I take a piece of copper, and right now you see nothing, but see what I can do about it. Okay, it's just lighting. Here. Turn off some lights here. Okay. So what I have is I have an electromagnet. Okay, we can see the pole here. The shiny piece is the pole, and I put a piece of copper on it. Okay, like this, and I have a switch to turn it on. But I still want to play with the light so you can see it better. Here, like this. And the moment I push the switch, it's actually trying to lift it. It can't lift it, but it's pushing it away. Okay? On the other hand, if I put a say same thing with a piece of aluminum, see, it's pushing it away. Now what happens if I put a piece of steel on it? Pardon? It will attract. Now, so what happens with that story with the repulsion? Because it also induces a current in the steel. So what happens with Lenz's law? I think it's more dramatic if I show it to you sideways. So if I do it sideways, so let's say do it like this. I'll show you. Bend the wires. Okay, so if I hold the steel sideways, get to where I can see it, see it's attracted. Okay? So again, steel is attracted. Now, if I put the aluminum on it, okay, and I lean it on it, turn it on, it's repelled. Again, it's hard to see because of lighting, but here. Okay, again, I put the aluminum leaning against the steel, it repels. Okay? So the first question, why does it repel copper and aluminum, attract the steel? Because all three are subject to Lenz's law.
Steel is a ferrite material.
Steel is what?
It's a ferrite material.
So, but it's Lenz's law, there's a current induced in it. Yes?
Minimizing the reluctance because it's a magnetic material that opposes Lenz's law, I think.
Ah.
I guess it's two competing effects.
Very good. There are two competing effects. If the material is ferromagnetic, there's two competing forces. Lenz's law tries to repel it, but since it's magnetic, the magnetic field tries to attract it in order to minimize reluctance or maximize inductance. Okay? Now, in the case of steel is not a very good conductor compared to copper and aluminum. So in the case of steel is a very good ferromagnetic material, a poor conductor more compared to other metals. So because of that, the electromagnetic effect, the attraction of the magnetic field overpowers Lenz's law by a lot. Now, if you could find a material which is very conducting and a little bit magnetic, you can find a material which should be balanced. The force will be zero. Okay? Because in copper, it's not magnetic at all, so obviously it repels by Lenz's law. But you can find some alloy which is just a bit magnetic and actually wouldn't be affected because Lenz's law will cancel out the magnetic attraction. But on the most common materials, steel, aluminum, silver, gold, they're all repelled strongly. Steel is attracted strongly. Nickel would also be attracted strongly because again it's a high resistivity material, very little Lenz's law, very little current, but very magnetic. Okay? If I want to make the steel be attracted even more, let's say I measure the steel, but I want to make it attracted even more. Somehow I want to cancel Lenz's law on the steel without canceling the attraction. What do I do? You should know this by now. Think of motors, how motors are built. Yes?
Constructed of laminated.
Very good. Divided by laminations, because then you cannot have rotating currents. If this piece of steel here above the magnet is made of laminations, you cannot have a current going in a circle because it doesn't conduct. But magnetically it's still the same as long as the lamination, there's not much gap between the laminations. So it has to be laminated the right way, right? If I laminate it this way, it doesn't help at all, because each lamination can have a circle of current. But I have to laminate it, if this is a field B, I have to laminate it this way, because the current wants to make circles around B. So I have to laminate it this way. Oh, is that clear? It's only one direction of lamination which helps. Okay, so that's one reason motors are laminated, to avoid eddy currents. Okay, so this is a basic theory, how things repel, and okay, but what I want to show you, which is very interesting, now this electromagnet has two sides. Both sides look the same. Both sides have a pole piece, there's a coil inside around it. This side looks exactly the same. But the other side behaves very weird. If I put a piece of steel here, okay, hold on, like here, if I put a piece of steel, it attracts it like every electromagnet should. But if I put a piece of copper, here's a piece of copper, it attracts it as well. That's weird. I've put a piece of aluminum, attracts it as well. I put a thicker piece of copper, that's the same, a thick copper, attracts it as well. Okay, so in previous courses I offered the final grade A without the final exam for anybody who can explain it. But I think you may have heard the explanation from a previous course, so I'm not going to repeat the offer. But that's a very difficult question. I have to tell you, I saw that in a very old book, and I immediately ran down to my lab and built it, because it was so weird that it really works, and I couldn't resist building it right away. But it works. Okay, so you can actually build an electromagnet for non-ferrous metals, which is against any intuition. And the more you know about electricity, the more it's against your intuition, because you understand about Lenz's law and so on. So it bothers you more. Okay, so any possible explanations how it works? Okay, so it turns out, I'll take you step by step through it and see who gets to the explanation faster. If you open this coil, you find out that inside the core of this coil looks like this. That's what's inside. So one side of it, which attracts normally, is just a laminated steel core. That's a laminated core. You can't see the laminations. Maybe here you can even see it's laminated. So one side is a regular laminated core. It's laminated because it runs on AC, right? So everything running on AC has to be laminated. Now the other side has a huge copper ring. You can see the copper ring here. You can see the copper ring here. So the other side has a huge copper ring, and that's the side which does the magic. Okay, so that's the first hint. So what does when you take a pole of a magnet and split it in two, in this case it's split symmetrically, you split it and you take one part and put a copper ring around it. What happens? Come on guys, we just went through it 2 weeks ago, so I'm getting worried about you. Either you're too shy or really don't remember a thing, so please speak up to assure me you're just shy. Okay. So, well, let's start with random people. What do you think? If you put copper ring around a magnetic pole, there is a magnetic pole which is split, and you put a copper ring around one half, what happens?
Current to be induced.
Good. So what happens to the magnetic field? You have two magnetic fields. One is coming out where the ring is, and one is coming out from where there is no ring. What's the difference between these two fields?
One is opposing the other.
No, what about the phase of these fields?
You have a 90 degree.
So you do remember, you're just shy. Okay, good. That's reassuring. Okay, so why is the field coming out from the copper side 90 degree behind the field which doesn't have copper? Maybe we'll pick on somebody else. How about you? Why is the field coming out from the copper behind the other field? Well, you just you just learned it. So what the copper ring has an induced current proportional to the derivative of the field. Okay, d phi to dt. So if the field is sine omega t, the copper ring current will be cosine omega t. Okay, so the two fields are 90 degrees apart because the current in the copper, which is generating its own magnetic field, equals to the derivative of the original field. I mean, roughly, it's not exactly 90 degrees, but roughly, since one of them generates a current based on the derivative of the main field, and the current creates its own field, there will be two fields, not exactly 90 degrees apart, but they'll separate because one of them impedes the change of current. The ring impedes or fights the change in current. So in one end, the field or the current can change easily. In the other one, the field cannot change easily because it induces a voltage in the ring, which impedes it. Okay. So what we have here, we actually have here, we have two fields, one field in the middle and two fields on the edges, but the field in the middle is out of phase. Okay. Yes, go ahead.
Do you cancel out the induced eddy currents?
It doesn't, because you can't cancel out induced eddy currents because at some point away from here there is a field. This field is a sum of, say, 2 or 3 fields, but it doesn't matter, there's still a field. If there is a field and it's changing, there are eddy currents, so you can't help it. Now it's true that the field here is very different than the field on the other end, because this is a sum of 3 fields, but it's still a field which changes, you can't cancel the eddy currents. Okay, so I'll just move you step by step closer and see who gets it. Okay, so right now we actually have one field here which is 90 degrees behind the two end fields. Now, what happens if you have a field and a field 90 degrees behind it, next to it? Okay, let's pick on some other innocent student. So what do you think? What happens if you have two fields that are 90 degrees apart?
The current that they would induce would be also 90 degrees.
Okay, so what kind of field will be created? If you have two fields 90 degrees apart, side by side, what kind of field will be created? Think of a stepper motor, two-phase motor. If you have two fields, rotating field, correct, right. So, any two magnetic fields 90 degrees apart will create a rotating field. So since here in this model we actually have something like this. We actually have something like this, and there is a copper ring around this. Okay, so now this will be, say, let's call it phi1. This will be the same as phi1, and this will be another field, let's say phi1 at 90 degrees. Okay, so this is the same as having one coil position. Let's not talk about the coils. The field is somehow going like, it wants to go like this, or wants to go. It's hard to calculate where the field wants to go because these are at 90 degrees. But let's say the field is normal and wants to go back, connect to the other side. But the middle flux is 90 degrees away from this flux, so in between here there will be a rotating field. Because this in here is the same as if you took two coils and drove one with sine and drove one with cosine. The two coils don't have to be physically at 90 degrees, but at some point here, there is some point here which is 90 degrees from these two, and this point sees one field and a field at 90 degrees. So at least at one point here, there will be a perfectly rotating field. If you go away from this point, the field will be not perfectly rotating, could be elliptical. Elliptical meaning as it rotates, it changes length. So here at some point, at least one point, it will be perfectly rotating field. If you go away from this point, it may be elliptical. If you touch this point, it will be linear. Does everybody understand that? When I'm touching one end or the other end, the field is linear because I see mainly the influence of this pole. It's the same in a two-phase motor. If you have two phases, and let's say they have iron cores, if you touch right here, you see mainly the field of this. So you see mainly linear. If you touch right here, you see mainly the field of this. If you stand here, you see a rotating field. But as you approach one pole, it becomes less and less rotating. It starts becoming elliptical until it becomes linear. And the same way here. If you approach this, it becomes elliptical. Inside here, it's linear. Okay? So if you look here, inside here it's linear, inside here is linear. There is some space in the air here that at least at one point you can show easily it has to be perfectly rotating. As you deviate from this point, it becomes elliptically rotating. Okay? So let's see, maybe I'll draw one more time the field. So if I draw again the poles with a short-circuit ring. Okay, inside here you have a linear field, here you have a linear field at 90 degrees, and here you have a linear field. Here we said there is 2 points at least, which are also mechanically 90 degrees, where you have rotating fields. Okay? And actually they rotate like this. Now, if I go closer to here, I'll get elliptical field, here I'll get linear field, here again I'll get elliptical field, here I'll get linear field. If I go more this way, it's the same thing. I'll get elliptical field and then linear field. But some zone, it'll be a true rotating field. Okay, so, does this give you a hint? Okay, so now what happens if I put a piece of copper, if I put a piece of conductor in or near a rotating field? Okay, how about you? If you put a piece of conductor in a rotating field, what happens? Think about it. What's inside an induction motor? Piece of conductor in a rotating field. So what happens to it in an induction motor? What happens inside an induction motor? You have a block of conductor inside a rotating field. What happens to the block? See, no, you know, just don't be shy. You've seen an induction motor. It has something inside the rotating field. What happens to the armature when you turn on the rotating field? It rotates, right? Because the rotating field, because of Lenz's law, we just went through it, it rotates. Okay? So what happens here to this piece? It's trying to rotate, okay? But it's trying to rotate with the field. So in other words, this piece of conductor, it's trying to rotate with the field. If I put a piece of conductor on this side, it's going to try to rotate with the field this way, because this is symmetric. If one field goes this way, the other field goes this way, because it's symmetric. Okay? So now we're coming to the end of the mystery. So now if I have this shape, and I have this short-circuiting coil, now we know already there is at least 2 points, okay, where this is a true rotating field, and there are many points where it's not true rotating, but it's closed. Okay. Now, when I put a piece of copper, so let's say I put a piece of copper like this. This is a piece of copper or aluminum. This part is trying to rotate this way, because it's just like an induction motor. This part is trying to rotate this way because the fields are symmetric. Okay? So it means there is some zone here. There is some zone here where the net force is down. Now, okay? So that's very strange, because it's true that there is Lenz's law, which is supposed to repel it. But if you play the currents right, you actually get an induction motor. Now this copper is trying to stop the rotating field, just like an induction motor. Lenz's law still applies. This piece of copper is put in a rotating field. Because of Lenz's law, it's trying to stop it. Okay? But the rotating field is just pushing it along, just like an induction motor. It's repelling. So it's still repelling. But it's repelling it in this direction, which is downwards. Okay? So it's a very clever geometry, and you can see this will only happen in a certain zone. So if you put a piece of copper which is much bigger, like a big sheet of copper, at this side it will pull it up, at this side it will pull it down, so there will be no net force. Okay? But you can see that there will be a zone, and the zone is about like this, that anything put in this zone, okay, it will be repelled by the rotating field which rotates downwards, maybe not so high, maybe anything put in this zone. There is a magic zone that anything put in this zone will try to repel the rotating field, but because the rotating field turns this way, trying to repel it, it's going to be pushed downwards. Is that clear? Okay. Anyway, that's not an important device, but the principle it works is interesting because it's exactly the principle of an induction motor, but used in a very clever way. Yes?
Is there any application which is actually useful?
To puzzle students. That's the only application I found. But it's fascinating that it can be done, because I use it to show students not to say impossible too fast, because something which is not related to motors, but it's important to know that the easiest way to succeed in high tech is to think of something that everybody else thinks it's impossible, but you know how to do it, and then other people don't try because they think it's impossible. Okay? So, but the trick is you have to choose wisely, because if everybody thinks it's impossible and it's really impossible, then you're in trouble. Okay? So the trick is you have to be very careful when you say something is impossible. And there are many examples of things that people looked at and said, that's completely impossible, but turns out it was very easy, because these people were just not imaginative enough to see that it's not impossible. So this is a good demonstration not to rush to say that something is impossible, because if it doesn't violate any laws of physics, okay, it's not impossible, but it may be very tricky to do. I think the classic example is that in the 19th century there was a French philosopher, Comte, and he wanted to explain that some of the things in science are impossible. No matter how much scientists will work, we'll never know the answer. So the example he used, that he said, look, we can live a very long life, but we'll never know what the stars are made of, say the sun and the stars. And by coincidence, it only took 10 years before people knew what the sun and the stars are made of. And how did they know? Pardon? Spectroscopy. Because within 10 years, first, let's see who were the people. It was Bunsen, Kirchhoff, and the guy Fraunhofer. Okay, so within 10 years, Fraunhofer made the first diffraction grating, and Bunsen and Kirchhoff used it to analyze spectrums of flames, and understood that there is emission lines and absorption lines. So you see black lines in the spectrum where the material absorbs, and you see bright lines where it emits. So within 10-20 years, a combination of Fraunhofer's original work on spectroscopy plus Bunsen and Kirchhoff research that every element has a signature, people just took a diffraction grating, ran sunlight through it, and they could see the signature of hydrogen, helium, and then put it at different stars which emit or absorb. So basically within 10-20 years was clear what the stars are made of. So this is a good example why one shouldn't be very quick to say this is not doable at all. Okay? So anyway, there's many examples in technology of things. I think I gave you this example of two devices used in spy world. One is this device which can find any bug, even if the bug is turned off, if you remember how it works. And another example of a device which tells you that somebody is looking at you, even at night. And again, first reaction of people is this is impossible. How can I detect a bug if the bug is not turned on, right? A listening device. Turns out it's very simple if you remember the explanation how to do it. Okay? So this is a very good example of not to say too quickly not possible. But apart from that, I never found any use for it yet. Okay, good. So this is this. So now let's go back and summarize all the motors. So there is two things that I want to talk about motors that I haven't discussed before. And one thing is, for each motor, how do you reverse direction? And the second thing is dynamic braking. Okay? By the way, I just want to make sure, did everybody hand in the assignment? What are you waiting for? Okay. 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 Next time you come on time. You could have gotten 0 for the assignment. Okay, good. Okay, good. So the two things I want to finish up the motor section with is, how do you reverse direction for the different types of motors? So the easiest question is, how do you reverse direction in a rotating field motor? Everybody should remember that. What do? Switch two phases. Because if you switch two phases, it's the same as reversing the field. Okay? Now, what do you do in a two-phase motor? Because there are only two phases. If you take a two-phase motor, which is already wired, like it's a 3-wire system, if you switch the wires, nothing changes. So what do you do then? What I mean, if you have a two-phase motor, which is already wired, it's a 3-wire system, like wire, 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 and you switch, okay, it depends what you switch, okay? But here, if you switch both of those, nothing happens, because you switch both, because you have to switch one to reverse the field, right? You have to, sine and cosine is one direction, so you have to have sine and minus cosine. So what you have to do, you have to disconnect and flip the coil. I went through it. Okay. What happens in a PMDC motor if you want to switch direction? What do? Like all the toy motors, and how do you switch direction? How? Just switch the battery, because PMDC motor is very simple, because the magnetic field of the field is constant. It has N and S, which are by the permanent magnet. The armature, if you flip N and S, it's going to push instead of pull, and so on. So PMDC motor, you just switch the leads of the battery or the power supply. Now, what do you do in a series wound motor? How do you reverse direction? So series wound motor has a coil, which is the field, and then has an armature with brushes, which has another coil. This is a battery. How do you switch directions here? Because if this is NS, the polarity of this will be NS. Okay, if you switch the battery, all four will reverse, but the direction of force will not change. Because if this is N and this is S, they still repel or still attract. So how do you switch direction here? Pardon? Exactly. You have to switch either this or this. You basically have to disconnect the coil, flip the coil around, or disconnect here, flip this around. But if you flip both, it doesn't help, because flipping both is the same as switching the polarity here. It does nothing. Is that clear? Good. Now, let's say you have a series motor, but you want to be able to switch directions by switching the battery. Let's say you have like a toy electric train or some electric drill or something, and you want to be able remotely to switch direction by switching the power supply, but you have this kind of motor. What can you do? Yes? Perfect. Very good answer. All what you have to do is put this in a rectifier, so this will see the same direction. So imagine if you put the coil in a bridge rectifier. So bridge rectifier is something like this. Okay, it has 4 diodes. That's a standard bridge rectifier. Okay, like this. Okay, and now you connect the power here and here. Okay, so now when you switch the battery, this will always see the same direction because it's a bridge rectifier. This will switch direction. So now it behaves like a PMDC motor because the field is always the same direction, so it switches. Okay? Anyway, with diodes you can do lots of tricks like this in motors. Good. Okay, so this is switching directions in all motors. Now, next thing I want to talk about, which is actually not so important in servo motors, but important in tools and big motors, and this is dynamic braking. Okay? So even before that, I want to talk about something a bit related, is which type of motors are best for servo motors, because, and then we'll talk about dynamic braking. So for a servo motor, the best motor is that it doesn't behave as if it has any internal wind-up or backlash, because what you want from a servo actuator is that you can command it unambiguously to go to a certain position. The position may be measured by an encoder, okay? But you don't like a motor, for example, that when it reaches position it loses torque or things like this. So because of that, a synchronous motor, a purely synchronous motor, has some advantages and disadvantages as a servo motor. The advantage of a purely synchronous motor is that you can run it open loop, because you know where it is, you don't need a feedback. If you give it 10 cycles of sine waves, you know it will move so much. And that's what you do with stepper motors, because most of the time stepper motors are not used with any feedback. You just command them. But the downside of it is that, for example, a synchronous motor doesn't have a very good starting power, because we talked several times that when you apply the full frequency to it, it just vibrates. You have to ramp it up to pull it in, because the magnet has to follow the field, and if the field starts rotating at full speed, the magnet will just vibrate. So you have to design your servo that you control the ramping rates, which is basically a filter. If you have in your servo some voltage controlled oscillator which gives the pulses, or a numerically controlled oscillator like through software which gives the pulses to the stepper, you have to design it that it will never start with a very high pulse rate, because then the stepper will not lock. Now in a stepper motor it's not so bad, because usually in a stepper motor the difference between the starting torque or starting speed without ramping and the starting speed with very nice ramping is only about 2 to 1. So basically if you cut down the maximum frequency, you can start it at full speed. Maybe I should give you some typical numbers. Can somebody guess what is the RPM, the maximum RPM you can get out of a stepper motor? From the things you did, from the projects you did when you played with stepper motors, how fast could you make them go? Can you make it run at 3600 RPM like a synchronous motor? No, you know that not. So what can you run them at? At the best, with ramping and everything. Yeah, a stepper motor without ramping you can run at around 500 RPM. Of course it depends a lot if it has a current driver or a voltage driver and all the stuff we discussed. This is already with good driving, with almost constant current driving, okay? So that's roughly, and with ramping maybe 1000 RPM. So this is when you apply the sine wave straight, and this is when you apply a slow sine wave which becomes faster and faster. So it's not very fast, okay? On the other hand, as you recall, a stepper motor has surprisingly good accuracy, because completely open loop it will be much better than 1/10 of a degree. And the reason I mentioned many times is it has 50 poles, it achieves the benefit of averaging of all the mechanical errors. Now, if you want a higher performance system, so this was a stepper with 50 pole pairs. Okay, this is 50 pole pairs. Okay. And the accuracy, let's say, is 0.1 degree, including all errors. Now, what happens if you compare this to a true synchronous motor, like you have a 3-phase or a 2-phase true synchronous motor, okay, with a magnet, just 2 pole or 1 pole pair, okay, so So that's be one pole pair, 50 pole pairs. Okay. So if you take a motor like this, how fast can you run it? I know you haven't seen many of these motors, but maybe you've seen some special projects, spindles.
Many thousands of RPM.
Basically, there's no limit really. A motor like this can easily run 100,000 RPM. The limit is mechanical disintegration, the bearings. There are mechanical limits. There's really no electrical limits, because if the rotating field, you can make it run fast. Now, one reason you can say, why is there a limit here actually? Why would it run so slow? So it's a complicated story. One of the problems here is that since a full step is 1.8 degrees, the leg of the rotor behind the stator is limited to a fraction of a degree. Because think of it as if you have total 50 pole pairs and power angle can only reach 90 degrees, okay? So 90 degrees, that's a quarter of a cycle, okay? And this has, so it has 50 pole pairs, and you have to take one cycle and divide it by 4 to get 90 degrees, so it's 1/200th of a rotation. So the power angle on a motor like this, power angle has to be less than 1.8 degrees. It just happens to be by coincidence also the step angle, okay? Now, in a motor like this, the rotor can lag many degrees behind. Because here, because it's a single pole pair, the power angle can actually be 90 degrees. Okay, it's actually 90 degrees, so this can lag a lot more behind the field. If the field is running fast and the rotor is lagging, and also has less coils, less inductance. Because remember, if you have 50 pole pairs, you have to have many sets of coils, 50 sets of coils which are wired together. Because at the end you only have two leads or two coils coming out. So at the end the stepper motor looks like two groups of coils, but they have many windings inside. Now here you can put less windings, you only have one set of coils, so there's less inductance, and you're allowing it to drag behind a lot more. So for all kinds of practical design reasons, this motor can run very fast. Another way of explaining it, for this motor to run at 3600 RPM, you only need to feed it with 60 Hertz. Okay? Now, for this motor, for a stepper motor to run at 3600 RPM, you would have to feed it, for this motor, at 50 times 60 Hertz. So you'd have to feed this with 3 kilohertz. Now, it's easy to drive coils at 60 Hertz. The coils have a certain inductance, but the voltage you need to drive them at 60 Hertz is small, right? Because the Z is 2 pi FL. Let's say you have a given coil. Let's say both motors have the same coil size. For the argument's sake, here in a stepper motor, the Z will be 50 times higher. If it's the same coil, you have to drive it at 50 times the frequency, the Z will be very high, you'll need kilovolts of voltage to drive it. So for many practical reasons, for power angle, construction, inductance, this cannot run fast, this can run very fast. So this one can run up to, if needed, up to 100,000 RPM, usually mechanically, if it's limited by bearing life. But for example, this motor, you have this motor in every hard drive, and the hard drives run at 10,000 RPM. And this can run for many years. Okay, so for sure it can run forever at 10,000 RPM. And actually it can run at 100,000 RPM if you need to. The limit is just mechanical, but certainly the fact that all the new hard drives and some DVD players, CD-ROM, DVD read and write, they have 64x speed, right? So they run at 10,000 RPM as well. So even little things which are inexpensive run at 10,000 RPM with this motor. But in your hard drive or DVD, the software does the ramping. Because this has still the issue, if you apply to it 60 hertz at once, it wouldn't be able to lock in. So you still need to ramp it up. Okay? So because it's all driven by some computer, this is always ramped. Okay? You don't hear the ramping because the whole ramping takes 2 milliseconds. Right? If this is run at a few hundred hertz, the whole ramping takes milliseconds. So when you turn on the hard drive, the whole ramping is in the first few milliseconds. Okay, so if you want to build a servo with very high performance, it turns out it is better to take this motor and gear it down. Let's say you want some fine position and you want to be able to run it open loop. It's actually better to take this one and gear it down until you have the resolution you want, because it will have a lot more torque and a lot more power. Now, the fundamental reason why a motor like this, geared down, will actually have more power than the same motor in a stepper version has actually to do with some nasty detail in the magnetic field, which is called leakage field. Because if you look inside a stepper motor, you have these poles, and in a stepper motor, because there are 50 of them, they have to be quite close together. This is a winding. Okay, this is a winding inside. Now you have an armature which also has 50 poles, and let's say that's NS, NS. Now the flux which does the work is the flux which goes like this, from here to here. But there is also flux going like this, because these poles are very close together. Okay? If the air gap was 0, this flux would be much smaller than this flux. But because of mechanical constraints, there is a lot of flux which goes like this instead of going where it should, which is to the field. Now, the ratio of the flux which does the work and the flux which is just wasted, okay, this is waste or leakage, this determines the efficiency of the motor. Because think of this side. This side is supposed to generate flux going to the rotor, but it also generates flux which is shorted by the air gap. So this flux that you short still needs current to make it. Okay? So basically you can see, just to exaggerate, if you made a motor which looked like this and had a huge air gap, this is NSN, and this is again NSN. If the air gap is huge, it's easy to see the motor will have very terrible efficiency, because most of the flux will short and very little of the flux will go to where it produces torque. Is that clear? So in a real motor, you're trying to make this air gap as small as possible to increase efficiency. But if yes?
What is the actual magnitude of that air gap in real life?
Pardon?
What is the actual magnitude of that air gap? How small do they make?
Okay, so this depends on the quality of the motor, because this is a thing which increases the cost of the motor. Okay, so in a stepper motor, it's about 0.1, 0.2 millimeter. Let's say more like 0.2 millimeter. In a big motor, like industrial motor, it's like 1 millimeter, because a big motor is harder to make accurate. Now the real problem with that, you can make it smaller without touching, but then the motor will have irregular torque and cogging. Because imagine that this rotor is a bit eccentric. So imagine you have some rough stator, exaggerated, and a slightly eccentric rotor. So at some point the rotor will come closer to the stator, so the torque will not be constant, and the motor will make funny noises. So they increase the gap, not just because they don't want it to touch, they want the field to be more or less uniform. Right? So if the variations here are 50 micron, which is typical, you can't make the gap 100 micron, because the flux will change 2 to 1 depending on runout. Okay? So that's why typically for small motors that's typical, for big motors it's typical 1 millimeter. But think of the other thing. In a normal stepper motor, the standard size that is most popular, that's called the size 23. I don't know if you know, all motors have a frame size, and the frame size is a diameter in inches. That's kind of an old standard. Size 23 means 2.3 inches. So all the motors you have in your lab, almost all of them are called size 23, right? So it's 2.3 inches. So anyways, that's about 60 millimeter. So in this type of motor, the armature is only about 25 millimeter diameter, right? And you have to divide, so 75 millimeter circumference, you have to divide it by 100 because it's 50 pole pairs, right? So each pole is less than a millimeter. So even in a normal stepper motor, this is 0.2 millimeter, but this is only 1 millimeter. So you already have a lot of wasted flux. Now, if you made the same motor as 2 poles, there will be no wasted flux, because this will still be 0.2 millimeter, but the distance to the next pole will be 20 millimeter. Right? So here will be no wasted flux. So that's one reason. If you have less poles, you can make the motor a bit more efficient. It's especially obvious not when you go to 2 poles or 4 poles, but it's obvious when you go to 50 poles. The motor will inherently be less efficient. That's why stepper motor efficiency is maybe 50%, while a motor like this is 90%. So bottom line, if you want a high-performance servo, even if it has to go slow, it's better to use a motor with less poles and gear it down. I mean, these are all kind of fine details. I'm not sure you need to remember all that, but if you look, say, at a CNC machine tool, CNC machine tool doesn't have big steppers to move. It has little motors like that, little 2-pole motors. It still has synchronous motors. Most machine tools still use synchronous motors, but there are little motors with gearing instead of big motors with many poles. And the reason is that's cheaper. For the same performance, you can make this go much faster, and it's cheaper. It's not cheaper on a small scale. When you build a lab thing, a small thing, it's cheaper to use a stepper if you don't need the high speed. Okay? But if you build bigger machines, like a machine tool or a robot, you don't use steppers. Like industrial robots don't use steppers. The original ones use DC motors, which are very good, because they have all the advantages you want, but they have sparks. Okay, so the original ones use DC motors. Some modern ones use brushless DC or synchronous motors, but gear down rather than steppers. So functionally, a synchronous motor and a stepper is exactly the same motor. But practically, when you start analyzing efficiency, torque, maximum speed, they behave a bit different, because this increasing the number of poles to so many poles has some penalty on leakage flux, on efficiency, on maximum frequency, on a whole bunch of penalties. That clear? Good. Now, okay. So one other thing you have to remember, that the fact you can run a stepper and these motors open loop is a huge time saver in development time. Because if you have to design a servo, a fully closed loop servo, versus a stepper motor, which you just give it a command and it goes there, the development time is almost 10 to 1. Because in a stepper motor, there is just a computer which commands a microstepper. The microstepper pulses the stepper, and you're done. If something doesn't work, you can put a scope after the computer, after the microstepper, and analyze it. In a true servo, it drives the motor, it goes to some encoder, and it feeds back. And it may not work, and you check out the motor is fine, the encoder is fine, the computer is fine, it still doesn't work. Because it's closed loop, so it can oscillate, it can do all kinds of things. So when you try to debug it, if something is truly closed loop, you have a much wider range of possible problems, like oscillations. Say if you have open loop, you cannot have oscillations. It can either move or not move, that's all. Okay, so if it doesn't move, you find out why. Okay, but it's a very simple system conceptually. It cannot have very strange behavior. While if you close the loop, there could be very strange things which take you a long time to figure out. A good example is backlash. If you have the slightest backlash in the system, open loop, it has no problem. If you have a stepper motor driving a lead screw with backlash, there's no problem. All what happens when it reverses, you'll get a small position error. But if you have a closed loop servo, like this motor driving a lead screw with backlash, you will not be able to close the loop. because the backlash inherently will cause the system to oscillate. Right? Because if it reverses, it doesn't want to reverse, the gain goes up, it reverses too much, it starts hunting back and forth at about 2 to 3 times the backlash. Is that clear to everybody? Good. Okay, so now we're going to the last subject on motors, and this is dynamic braking. And as I said, dynamic braking is not so important in servos, because usually these are small motors. You are not so interested in conserving energy. But dynamic braking is very important in big motors for 2 reasons. The first reason, you want to conserve energy. Like if you have an electric car or even electric bicycles today, you want to recapture the energy right downhill. And the second reason why dynamic braking is important is safety. If you have a big machine and something happens, you want to be able to stop it right away. And if the machine doesn't have brakes, it's very important to be able to apply electrical braking to it. Like a machine tool or anything, that table saw, that you want to stop right away. Okay, so let's talk a little bit about it. So there is 2 aspects of dynamic braking. How do you actually brake it, and how do you brake it with recovering the energy? There are 2 different things, right? Because if you have a PMDC motor, say, if you have a PMDC motor and you run it from a battery, okay, this is how do you actually brake it? If it runs up to full speed, you want to brake it, what do you do? Turn this off, we don't need this system off. Okay, so how do you brake a PMDC motor?
Turn it on.
Pardon?
Turn it off.
Okay, if you turn it off, it's going to coast to a stop because it has inertia. Say, think of your hand drill at home or power saw. When you let it go, it slows down, but it doesn't brake sharply. Yes? Okay, so the fastest way to brake it is the reverse polarity, but this causes a huge current spike, which I'll explain in a minute. But there's one step which is less dramatic or less drastic. All what you have to do is short it. So if you wire the circuit like this, if you wire the circuit, you have a battery, okay, you have a battery, and you have a ground, and you wire the switch that it can either connect to the battery, and if you want to break it, you move the switch to the ground. Now, if this is spinning in a magnetic field, it's a generator. So the moment you connect it to ground, you are putting a short across a generator, then by Lenz's law, there is an induced current, it wants to stop. Okay, it's basically, to make a current needs a torque. If you short it, it's making a huge current, so it needs a huge torque, and that huge torque slows it down very quickly. Is that clear? Good. So this is braking for PMDC. Okay? Now, what do you do if you have a series wound motor? It gets a bit more complicated. Okay? Because superficially, if you just spun it and shorted it, so again, if you do battery, if you do and ground, so if you look at this superficially, it wouldn't work here. It wouldn't work here because there's no permanent magnet, so how will it generate electricity? But it turns out it does. The reason it does is at the moment you stop the current, there is still some magnetism, and also everything has a bit of residual magnetism. So when you switch it over, even if there was no current, there is a bit of residual magnetism. The residual magnetism starts creating a current, and the current increases the magnetic field. Okay? Because even if there was a little bit of magnetism left, a current will start flowing, the magnetic field will go up, and it will increase the current and still brake, but not brake as well as this. Because this starts braking at full torque right away. Okay? And okay. Now, remember the model of this, the current is not infinite, because the model of all these motors, there's also some resistance. Now, if you So this will be much less efficient in braking. If you want to make this efficient in braking, you really should supply some current to this when you brake. You should short the armature but supply current to the field. Okay? So say if you can do this, if you can short the armature but use the same battery to power the field, it will be much better. Okay. Now, what happens about the suggestion was here, reverse the battery? Now, the problem with reversing the battery is this. The I on the motor is V minus EMF divided by R. Okay? And typically, the VMF is almost as big as V. The reason we know that, because we know the motor is efficient, so the voltage drop on the resistance is 5–10% of the total voltage. Otherwise the motor wouldn't be efficient. So this is a normal current. Now when you short the motor, V disappears. Okay? So then you have just EMF over R, which means the current will go up tenfold. Because typically EMF, if this is 100%, typically EMF is like 90% of V. So this is V minus EMF is about 10% of V. Divided by R gives you the current. But if you short out the motor, the current goes up ninefold. Okay? The same thing happens when you start the motor, because the moment you start the motor, there's no EMF. That's why all these motors, when you draw the starting current versus time, they all start like this. They all start with a huge current spike because there's no EMF, and we talked about this before. But if you reverse the voltage, let's say that instead of V, you put minus V. Okay, so if you reverse a battery, you get minus V minus EMF divided by R. So now they are in the same polarity, the current will be 20-fold. Okay? So that gets a bit dangerous. So you can brake a motor fast by reversing the input if it's a PMDC, but you'll get it, instead of a 10-fold current, a 20-fold current. Okay, so these are DC motors. Now DC motors are very easy to use for regenerative braking. If you want to recover the energy, all what you do is you don't connect it to a short, but you connect it to a DC to DC inverter. Now, you know that you can make a DC to DC inverter which accepts any input voltage and outputs a constant voltage. For example, your computer power supply. If you look at your computer power supply, it says you can give it anything from 90 to 280 volt or to 240. So what it does, it rectifies the AC and uses a PWM chopper to adjust the duty cycle to the voltage. Right? So if you think of your computer power supply, it looks like this. The line comes in here, then it has a rectifier. It's actually a bridge rectifier, but symbolic in a capacitor. So it makes a DC, and the DC depends on the input voltage. If you give it 100 volt, it will make, if you give it 100 volt input AC, what will be the DC voltage? If you, how much?
71?
No, 140. Because if this is a sine wave and you call it 100 volt, the 100 volt is not the peak, it's the RMS value. Okay? The RMS value is 0.707 of the peak, so the peak is actually square root 2 times the line voltage. Right? So if you did this, if you connected this to 100 volt, the capacitor will charge up to 140. Okay? Now you put a chopper, PWM chopper, which changes the duty cycle of the pulses to give you the DC voltage you want. And the chopper is controlled by sensing this voltage. So it doesn't matter what this voltage is, the output voltage is constant. That's how all power supplies in the world work, right? Now, the same circuit, if you connect it on this side, instead of connecting it to ground, if you take this and connect it to this point, you can convert this voltage to a DC voltage no matter how low it is. So now we'll redraw it. Okay, so we redraw it like this. We have this is an armature. This is a coil in the armature. This is a PMDC motor. Okay, now it has some resistance, has poles NS. Now here you have a battery. Okay, here you have a battery and you have a switch. Okay, so this is a switch. So let's draw it the other way, like this. You have a switch. When you close the switch, the motor is running. But when you want to stop the motor and recover the energy, you switch it to this, which is now not to ground, but you switch it to PWM chopper, which is the same as connecting it to this point after the rectifier. You don't need a rectifier because it's already DC. So you can switch it to PWM chopper, which connects, and inside you usually use a transformer to boost the voltage. Like sometimes this voltage has to be higher than this voltage. So what you do is you chop it first to high frequency AC, goes through a transformer. So sometimes there's another stage here. Yes?
Don't buck boost converters also, like, can you use them to increase or decrease the
Yeah, but that's just a flavor. But in more generic case, you change the voltage. In most generic case, you have DC here. First, what you do, you make it into AC. You say DC to AC. Now you can run a transformer. So actually, the power supply of your computer has this transformer, mainly for safety, because you want to isolate the line from the output, and also because you don't want to chop at a very low duty cycle. So inside your computer, it takes 140 volt DC, first converts it through a transformer to maybe 20 volt AC. Then it rectifies in PWMs. Okay, then you have a rectifier, then you have the PWM. Okay, and then you connect it to the battery. Like this. That's a PWM. So this whole part is exactly like your computer power supply. Okay, so what happens when you put it on brake mode? When you put it on brake mode, the voltage versus time looks like this, because the motor is slowing down. But at any point here, you can capture the energy because you adjust the PWM. Because you want at any point in time this voltage to be higher than the battery. Right? Because you want to charge the battery. So at this point, the PWM outputs some very narrow pulses. At this point, it outputs wider pulses. And at this point, it outputs very wide pulses. So the average voltage at the output is always higher than the battery voltage. So all the energy till the motor stops is recovered and put in the battery. Is that clear to everybody? Good. So that's basically how dynamic braking works. This is how it works in your bicycle when you have some new electric bikes have dynamic brake, regenerative, not just dynamic, regenerative. When you say dynamic, you just mean this typically. That is called dynamic braking, and that's called regenerative. You actually put the energy back in the battery. Okay? So of course in electric cars that's critical to get the maximum range. So next week, I didn't have enough time today, but next week I'll explain how this works in an induction motor, because that's actually quite tricky. It's very easy to understand how this works in a DC motor. It's very easy to understand how this works in a synchronous motor, because synchronous motor is just like a generator. It's actually not so obvious to understand how this works in an induction motor, because the induction motor has no magnets. Okay? So think about it, and I'll explain it next week. Okay, thank you.